Wood block printing is 280. And then jumping to wood and metallic ceramic printing, lithography that all of you would have heard, that lots of ancient empires used to do their own artistic stuff. Color printing started in the 1800s, screen printing 1900s, photocopiers became common in 1960s, and then a whole series of printers that we use for common applications, dot matrix later, and then 3D printing around 2010, mostly do the plastic extrusion kind of things. Again, same thing that he talked about. Dr. Surya made it to 7 different types. Here are 5 different types. Again, depends on who you ask. Different types of 3D printing, right? You have a printer, you have a material that you need to print with, you have the shape that you're printing, depending on what is your final application that you want. So that's what it is. So 3D printing or additive manufacturing, one of those techniques, as opposed to subtractive manufacturing. There's another thing with subtractive manufacturing. So if you see a carpenter make a wooden object, it's subtractive manufacturing. They take a block of wood and they carve the shape out of the wood by removing piece of wood. Or a sculptor doing a stone sculpture is subtractive manufacturing, where you subtract things. Whereas we are talking about additive manufacturing, putting things together. So additive manufacturing, that's what Professor Surya was talking about, layering things one on top of the other. Subtractive removes the material. Some examples for additive was subtractive manufacturing. A little more repetition of what you've seen. Again, types of additive manufacturing, you saw all of this in the previous slide, so I will not go through it in detail. We'll get into more of concrete things. Binder jetting, one of the additive manufacturing techniques that you saw earlier, is used in, I wouldn't say structural engineering, but kind of civil engineering, soils, for example, right? You use binder jetting using sand and soil to create soil and sand structures, not structural shapes, but things that you can use with soil. So binder jetting is also one of those things that they use. Extrusion-based additive manufacturing, that's what we're going to spend a lot of time on. That's your chocolate molds that you make of the pasta that you see is actually an extrusion made. So if you see this shape of pasta, if you go to a restaurant and get it, that's an extrusion-based food product that you get. Architectural structural shapes, you can get lots of different structural shapes. And one of the things that in civil engineering, structural engineering, that you get with additive manufacturing is the flexibility with structural shapes. As civil engineers, you all know that shapes are important, right? But we are all restricted with the kind of shapes that we can use. Prismatic shapes is all that you've learned. You probably have learned 3 classes on reinforced concrete design. You probably designed only rectangular beams and at most rectangular and circular columns. We never did any other shape. We also learned ever since our first class in structural engineering materials, concrete is strong in compression, weak in tension, but we have steel comfortably to put in concrete to make a reinforced concrete structure, tension, compression taken care of. But in the process, what we do is we put a lot of concrete in places where we don't need anything at all, right? We waste a lot of material. So now, with the sustainability angle, we don't have enough resources to make large structures. Countries are developing at such rapid pace. India is developing, China is developing, Africa, tremendous development. Where do we get all this concrete from? And even in India, if you look at it, you don't have enough sand now, right? You have paucity of sand. Natural resources are at a premium. So to conserve resources, concrete being one of the most used materials in the world, we need to conserve resources. We need to make sure that we need to put material only where they're actually needed. So along with shape optimization, you can do the structural optimization to put concrete only where we need them, not put randomly. For example, if you do a reinforced concrete beam, you say that below the neutral axis, concrete does nothing, right? It's all the steel that does if it's a simply supported beam. So in those kinds of systems, can we do the shape optimization? Can we do? So the bridge that Professor KVLS has printed here, shape optimized to make sure that you put concrete in only the places that you need. That's another major advantage with concrete additive manufacturing. So if you're thinking of building another house exactly like the house that you have, a rectangular shape and building, probably not much of use. But if you want to use a unique shape where you optimize the material, you optimize the geometry, you can save 30-40% of material, you make the structure work harder in locations where you want it, this becomes a useful technology. So you see lots of different shapes, lots of different architectural shapes. That's a seating chair, kind of a bench, kind of a thing. A wall geometry. You can save a lot of material by doing a wall geometry. You can have bracings for the wall like this, and you can have thinner whites for walls. If you're building a concrete wall, you can actually start to save material. You can also shape the wall in different ways to do unique structural functions. Probably later in the class, in the session, we'll see that as well. So that's concrete 3D printing. This is one of the bridges that was built in Europe some time ago. Another picture of how you can actually shape a building in a unique way. AI is everywhere, so I thought AI can also generate some 3D printed buildings. So I asked AI to generate a 3D printed city and in concrete. So it actually created a concrete ball first and built city on top of that. Maybe it thought Earth also can be made of concrete, right? AI's imagination can't question. Automation. The other advantage for 3D printing, again, so all of these are advantages that we have not completely made use of yet, right? So these are all potential advantages that we all can make use of in situations that we can make use of them. So these are not technologies that are show me a 3D printed structure that is like this. No, you won't find it, right? Somebody will have to build it. It has to develop. But automation has created lots of advances in civil engineering profession, especially in the Western world where labor is ridiculously expensive. In locations where labor is cheap, this might not seem to be such a great advantage. But in the US, for example, where if you have to spend $1,000 on something, for example, if I have to do, so I learned a lot of things that I would have never learned if I were in India. For example, I can do reasonably good level of plumbing at my house. Okay, I can fix reasonably decent stuff. I can fix garage doors when it's broken. I wouldn't have done this. The reason I learned it is if I call somebody to fix it, he'll come only a week or 2 weeks late, right? Because he's so busy, they have so much of work. And then he'll charge me an arm and a leg to do something so simple. Even to just come in to look and tell me what the problem is, that's $150. So expensive. Labor is so expensive, and specialized skill labor is not very easily available. So if you are a plumber, there are in Australia, for example, lots of students who went to study business and marketing are not getting jobs after their 2-year degrees. And what the Australian government is telling them, look, you're not going to get these jobs. We will now pay you 6 months if you're interested to join a skilled labor course, carpentry, plumbing, masonry. We'll pay you to do it 6 months to do a course, and you can stay back after you're doing your MBA. You can be a mason, for example. You'll actually get more handsomely paid. Do you want to do that? That's what Australian government is asking lots of foreign students who are going there. So automation is such a handy thing when you don't have people to do the work. And that's another one thing. And in the US, budget overruns and cost and time overruns are standard in every project, right? So how do you control that? Can automation control some of that to take care of dull, dirty, and dangerous? That's not a really good politically correct word, but this is what they do. Dull, dirty, and dangerous rhymes also nicely, right? You can say D, it starts, all three starts with D. And these are things that you don't get people to do the work. Can you automate them? Benefits are there. There's lots of money spent on safety, on worker safety, right? One life lost is a life that's you're never going to get back. So there's no value that you can put on life. Of course, there's insurance companies that will pay you whatever amount of insurance for the life lost, but realistically, you can't put a value to life loss. So safety is paramount. So any minor accident is treated as a major thing, and companies and construction companies take pride in saying 1,000 days without an accident. You'll see this big boards in, if you go to construction sites, 1,000 days without an accident. So all of that. So those are critical. So all of those benefit from automation. So if you can make construction automated, the downside is in a country like India, a lot of people rely on construction labor, right? So you're taking a lot of labor off. But again, I'm talking about situations where you don't have that. Automation is a good thing. Construction productivity has declined. This is World Bank's report in all fields from 1990s to 2020s. If you look at it, productivity has increased. Construction productivity has come down. There are several reasons. You can't just blame the people for that. There are several reasons for why that is. But pretty much every other industry, you see an increase in productivity, whereas construction, lack of productivity. How do we account for that? Um, Again, same idea here. Industries like media have seen the most digitization productivity growth. Construction is at the opposite end of the spectrum. If you look at digitization score, very low digitization score, very low growth rate, very low growth rate. Right? So how do we make, so one of the ways to make construction more of, if you think of construction as a manufacturing process, if you think of constructing things as a manufactured process, because quality for a prefabricated product, for example, right? The quality that you require is like a manufactured product. So can we make these processes better? Lagging construction productivity costs the global economy $1.6 trillion a year. Can we correct some of those changes? And look at in North America, lots of, again, it's all driven by numbers, are American numbers mostly, so driven mostly by North American numbers. So three primary opportunities in digitization generally: automation of traditional physical tasks, like I talked earlier, robots laying bricks. In the 1970s, it was done. Machines paving roads. Every road is paved by a paver, right? If you look at massive highway developments now, you have concrete paving machines paving it, asphalt paving machines paving it. People don't pave it anymore. It's automated already, right? So you're doing it anyway. Rebar tying of rebar. So there was some study that was recently done in the US, and simply on a 1 mile of a concrete pavement, removal of rebar tying, the labor associated with tying rebar alone is $2 million worth of saving. Labor in a mile. So hugely labor intensive processes. Automation of modular construction production factories, including 3D printing of components. Can we do it? And there are ways in which, for example, can we do 3D printing of components that are repeating over and over again? And then digitization, automation of design, planning, and construction procedures. This is where the industry wants to reach. The entire digital construction industry wants to get there. The whole process, including design, planning, and construction. So there is this whole report that was put out by a digitization committee called democratization of construction. You basically say that I want a house of this design. Your CAD generates it. You can take it to a potential, probably 2050, 2070 year futuristic plant. You can take it. The robots will design that building. It'll be printed. It'll be given to you on a platform. You can take it on a platform and put it where you want. That is the dream of how you want the entire building, design, and construction process to happen. We are so far away from it, but at least some thought processes. So what they eventually want is integrated design and manufacturing and assembly, process innovation, optimized improvements, product innovation. So look at your constructed output as a product, right? So if I have a building, what are the components? I have walls, I have beams, I have columns, I have roof, I have my functional elements. plumbing. Look at each of those as individual products. And how do I improve the design, construction, and production of those individual products? That's the whole idea. And eventually, affordable, zero energy, healthier, uh, improving productivity, quality, affordable. So this is all the big picture where the industry eventually wants to grow. Several industry groups are putting out white papers as to how they want to see this in the next 30, 40, 50 years. And we are really at the starting point of it, and really learning to walk the walk. While in lots of other industries, additive manufacturing has progressed substantially, right? One of the major things, and Dr. Surya hit the nail on the head, right? If you really can't make something economically, as a civil engineer, you will know your product is not going to be sold. Nobody in the civil engineering industry wants an expensive product. You want it economically. Even in mass construction, there might be niche consultants, niche clients who would want it, but generally, unless you're economical, then what's state of the art, you're not going to make headway. Or your product should have such unique qualities that you should be able to make use of. And so the way that you do in 3D printing, the way that you can actually make it economical is to save materials from a conventional construction point of view by doing all the optimization, for which you need to understand how to design, what are the properties of the material, where do you put it, how do you put it. So it's going to be a collective process. Here is how the life started. 3D concrete printers, if you look at it, this is where it was 10, 15 years ago, and we've come such a long way now, from really people printing mortars or paste in a very small form. We also have done it. That's the process. That's evolution. This was, oh, sorry. This was the first printer that I bought. Again, a 3D printer. Every part of this is 3D printed. That was, I don't remember how much. The company is out of business now. They don't even make it. It was an extrusion printer. And then I don't even remember the number of. So we got, in the university, I was buying these syringes like crazy for printing, right? And our business office came and questioned. They were thinking I was doing some drug business in the lab on the side by buying massive number of these syringes, these barrels and dies. So this was what we started with, but we've come a long way. There are now very fancy printers, robotic arms, gantries, all of those that you can do. You can have extrusion-based printers, you can have frame-based systems, robotic arm systems. Frame-based is your gantry ones, robotic arms is the one that Simply Forge also has. If you go to the field trip, we'll see that. There are several different types. The cable robot and concrete extruder. This thing was there. Oak Ridge National Lab in the US came up with this very nice cable controlled one that could do it, but it wasn't really popular. Icon is this company in Texas which actually built about 200 houses, 3D printed houses in a big 3D printed park, and the company is almost going out of business after doing all of that. But they came up with their 3D printer called Vulcan, which is a gantry system, but a much more bulkier version. It's a very unique kind of a system. Apriscore came up with this thing where you can have a kind of a space thrust kind of thing that prints concrete. Um, this was the older version of the robotic arm that you can see here now, much more sophisticated, much more complicated at the edges. But if essentially what you're doing is you're mixing whatever you want, you're putting it in an extruder, pushing it out, and then eventually it comes out on the side and you want to build it, layer it, print, layer on top of it. And you will see that if you want to print concrete, conventionally we use formwork because concrete is a flowable material. It flows, it doesn't retain its shape, and therefore we need something to contain its shape until it sets and hardens. Now we have the requirement that as soon as it comes out of the nozzle, you want it to be shape stable. And then not just shape stable, you want the layer to be printed, you want the next layer to be printed on it quickly, you want the layer on top of it to be printed quickly, you want to be adding superimposed load very quickly. Whereas in the conventional set, you will say you put the concrete and go home and come back after 3 days or 7 days or whenever you want to put the next load on top of it. Now the loads are added instantaneously, which means the structure should have the strength to carry the superimposed loads without collapsing, which means the fresh state properties of concrete will start to control a lot of what is happening when you print concrete. Unlike plastic, where as soon as it extrudes, you will see that you would have seen pictures where it solidifies. You are applying heat to solidify it, right? Or you're applying some kind of a or a thermal impulse or an optical impulse, a light to solidify it. Whereas you don't have the flexibility to do that. You can't take a giant heater and go right next to concrete. Even if you can take a giant heater and put it next to concrete to make it set, it will give you lots of other problems as you go through. So you really don't have that option. You need to make the material itself do that process. So you have to control your hydration, you have to do all those. That's what we will spend a good amount of time probably tomorrow on how do you control the early age property. So that's pretty much what it is. That is aggregate bed concrete printing. This is something that's coming up now. So you basically put a layer of mortar and then you just layer some aggregates. The next layer comes in. So you can, people complain, oh, concrete 3D printing, you're printing only mortar. It's not even concrete. No problem. We'll make it concrete this way, unless if you have a printer with a nozzle that is large enough, with a blade that's large enough that can handle aggregates. Now there are printers that can handle 10 aggregates fairly comfortably. The problem is that the printed surfaces will look very ugly if you have aggregates. Mortar printing looks fairly nice. Again, going back to a few other concrete printers, and the price of those printers, you can see 1.8 million, $500,000 worth of well, some of them, of course, have come down a little. Cobord is one company that is, let's see, popular all over the world now. They have pretty much a good US market. They have lots of markets in Asia, in Southeast Asia as well. This is what IIT Hyderabad and group has printed. This is the IIT Madras supported group. So again, you'll see this like little pockets in India coming up with collaborating with companies that manufacture printers, developing materials, and you'll see that. And it's actually in civil engineering, we really haven't seen this if you look at it, right? Where a technology develops from, you will see this a lot in computer science, you will see this a lot in electronics and semiconductors. Lots of semiconductor chip advancements have come from companies, Berkeley and Stanford. Those are the places where, so if you look at Intel, Intel would have gotten the patent, but some of those fundamental technologies they would have taken from Stanford or Berkeley or Carnegie Mellon, places like that. Whereas in civil engineering, we do research after somebody figures out that they want to construct something like that. We pick it out and say, can we make it a little better? We are all about incrementally making it better, right? But this is one where it's fundamentally started from academic institutions and then has branched out in most countries. And most groups have places like this that they have worked with, right? So this is a cantilever column. You can see the layer by layer printing process that's being done. Lots of applications. Again, we have some castles being built. This is the U.S. Army Corps of Engineers built this soldier huts kind of things. They did this in about 2015-ish, so about 10, 15 years ago. This is IIT Madras's first demonstration of a printed building, but this was printed in about 4 or 5 different pieces and stacked like you do bricklaying. This is again another U.S. Army Corps of Engineers project. This is I think it's somewhere in China. They've done this, and lots of examples of printing. This is the first house that we did in Tempe in 2018. This is the first permitted house in the US. Permitted meaning a city approved construction of a 3D printed house. Until then, there was no permitted houses. So you're not, if you can build, but if you live in a house that's not permitted and something happens to you, no insurance company will cover you. And if you understand the situations of living in the US, if you don't have insurance, you better run away to somewhere else, right? So this is the first permitted house that we built in Tempe. This was built using a cobalt printer. This house, it's about an 1,800 square feet house built by Habitat for Humanity for a family that registered with Habitat for Humanity about 5 or 6 years ago. And among the families, there was 200 families, homeless people registered with Habitat for Humanity. And then when they said we are building a concrete house, nobody wanted to live in that concrete house. Everybody wanted their traditional wood framed house. US, it's all wood framed houses, right? They wanted only the traditional wood framed house. Nobody wanted this house. And finally, they got a family to live. And this house was supposed to be built in Arizona in February, March timeframe. The printer had to come from Europe, was stuck with customs in Texas, did not get to Arizona till May. In May, in Arizona, temperatures go to 40 degrees Celsius. So they were trying to print this at 40 degrees Celsius, and in 4 layers, the whole thing is cracking left, right, and center. Right. So then we had to go in and do lots of testing to change the mix and to change the curing processes. But eventually, it came out decent. Again, remember, this is 2018. 2018 is infancy of 3D printing still. So you will see they're not very good. So inside was all plastered because the family who lived there said, we're not going to live there until it is all smooth and nice. So they had to plaster the whole thing. But eventually, it was a nice experience. We did a lot of testing in our labs for cracking, for strength development. Strength was not developing. Because the city wanted strengths that are much higher than allowable concrete strengths because there was nothing in that. So they want to be safe. They said without 4,000 psi, we're not letting you print. And then to get 4,000 psi on a mortar, which was cracking left, right, and center, was challenging. And this is the architectural drawing of that Habitat for Humanity house. This is the post office that was told by Professor Surya. This is in Bangalore. I think this is L&T built it with IIT Madras. This is Tosta built it somewhere in Chennai. This is the first house that IIT Madras built in their campus, but they have completely plastered it because this outside surface wasn't looking all that great. And this is, all of you know what this is, all familiar faces. The bridge right here in the campus. So for people who have not seen it, you're taking them there, right? At some point of time, you will see the bridge that's in the campus. And this is the latest one that Professor KVLS is claim to fame. This is the Indian Army's thing that it was last week. It was the news last week in the newspapers last week. So beautiful tiger structure. Again, you look at it, if this again, by the time I cut and paste, it's not good. But if you really look at the computer, the nice features on the face of tiger is actually pretty good. And you will never get it in any other form, or you will have to spend so much of time to make a mold for it to do it, like Dr. Surya said earlier. So low volume, high resolution, pretty good. Um, Overview of major advances. So we can do shapes. This is how we reinforce 3D printed concrete, right? So in the house that we built in Tempe, the concrete wall was simply they said we have to have 4,000 psi, but the wall that the double white wall was not supposed to be carrying any load. Every 10 feet you had to put in a column, you had to put in rebar, physically put in rebar and grout it so that these are all columns. And then the walls are simply there. It'll take a lot of load. 4,000 psi concrete is 4,000 psi is what? Close to 30 megapascal. 28 megapascals or so. It will carry a lot of load, and walls 28 megapascal is huge, right? 15, 20 megapascal is more than sufficient for walls. But we had to do that for code. So that was your initial way in which you reinforced. Reinforcing still is a big unanswered question. We'll spend some time on the last day talking about some challenges. No real solutions, but some potential ways to take care of that. Um, Solid geometry. This is such a solid geometry. Think of how much weight this will have. Think about that. If you build something like that with solid geometry, it's going to have tremendous mass. And how do you do it? That's a vertically printed panel component. So now you start to make allowances for um, hollow spaces in between and start to reinforce those hollow spaces. Because you really can't reinforce with steel, it's going to be very difficult. You try smart ways to reinforce it with grids itself while you print, that you can do in different ways. You make use of the geometry, you understand the load paths, print where the load paths are actually so that the load goes through that. You can do a lot of those things which you are not able to do with conventional print. Okay? All right. Before we get into real cement based materials, any questions, comments, anything that you want to? Yes. Yeah, it was a concrete foundation. So foundation is all done. It's all concrete mat foundation. So just a concrete mat. In Arizona, because of the type of the soil, you always need a post tension foundation. So it is always a standard way that you need foundations for that. So it's all post tensioned. Other questions? All right. Is this pace good? Am I going too fast, too slow? Let me know if it's too fast. Good, right? Let me know if you need me to change the speed or whatever. Okay. Now, for concrete, what do we need? A few things we talked about, but kind of getting into the nuts and bolts of what it is. 3D printing by extrusion is what we're going to deal with. So forget about the remaining 6 different things that you saw earlier. Those are all important things for different materials. Right now, we'll talk only about extrusion. 3D printing by extrusion, layering through extrusion. That's what we do. What do we need first? The concrete has to be soft enough to be extruded, correct? You need it to be soft enough. Anybody who has extruded, anybody who helped your mother in making any of those South Indian delicacies, murka, things like that, if you've helped them squeeze through, you will know, right? You have to have it soft. What happens if you don't have enough water in that dough? You will have to put in a lot of force, and then whatever comes out will be cracked. So you have to have the material soft enough to be extruded, and to intermix with the previous layer. Because if it is not soft enough, you've put one layer. If it's not soft enough, it will not really bond with the previous layer. So you have to have soft enough. But then once it is soft enough, can it support the previous layer then? No. But then what you need is to have the property development fast enough to be able to support its own weight and weight of the superimposed layer. How do we do that? And that is the whole idea of playing around with rheology of concrete. So lots of people who work on 3D printing of concrete, or who has to do anything with 3D printing of concrete, will spend invariably a lot of time with the rheology of concrete, very similar to what people did when they started to pump concrete 20, 30, 40 floors above. Right? You can't carry the concrete all the way. You wanted to pump it. You had to make the concrete fluid enough in a way that when you get to the 30th floor, still you are getting the paste and the aggregates as one homogeneous mass, not the paste coming first, the aggregates following later, or vice versa. Right? Lots of advances in admixtures happen because of that. Lots of advances in pumping technology. What happens when you have high shear flow within a pump? We never had to do that with concrete. All you had to do was mix in a mixer and place it right there. You never had to know what happens when you pump concrete through long distances, right? Pumping high shear flow. The whole idea of shear flows came through. We will use all of that in our understanding of how um, you can 3D print concrete. Finite waiting time between layers. If I can print one layer and go home, come back and allow it to develop strength before I print the next layer, then if I have 1 centimeter or 2 centimeter thick layers, by the time I build 3 meter tall wall, it'll be 6 months, right? I could do something else. So you can't afford to do that also. You have to have a finite waiting time. The waiting time has to be a shorter period. Yield stress change from layer to structure. We'll talk about the idea of what yield stress means. You would have seen yield stress, yielding when you did the experiment with steel, tension test on steel in your undergraduate class. You would have seen the yield stress, right? Fresh concrete also yields slightly differently. We'll see what that is. Rate of build-up. How quickly can you build layer after layer? How much time do you have? And that is now something that's intricately linked with the process. So if I have to build a rectangular shape, I need to know how big of a perimeter I have and how fast I can print, so that by the time I come back to the original shape, original location, a certain amount of time has passed by which the initial concrete that I have laid has some strength to carry the next layer. You see that? So your printing path, how do you adjust the printing path? If I'm building building a building with several different walls and all of that, what path is the optimal path for me to do it, so that when I come back after one layer of that whole thing, I'll be ready to print the next one. I can't be too quick because this one will not take the load. I can't be too late because this would have dried so much that there won't be good bond. Right? So again, questions that we have to answer. So lots of open questions that you have to think very differently from how you would design conventional concrete. So again, some more pictures of what it is. So you think about the material, think about the mixing process, which is happening within the printer, and then all of this is condensed here. So you're taking away all of these steps, right? The sequential process, laborers, tools, none of those. Your printer is doing this whole process. Plus, eventually, less waste because you have designed it correctly. Your computer is doing it, and it's all done systematically. Process steps involved. This is some of those. You have to do the design, 3D model developed using CAD software. Different 3D printers come with their own software, their own ways in which you can do it. Several open source programs are available that you can go and do it and interface with your printers as well. Slicing is a process where the 3D CAD model is broken into layers so that the computer knows that it is a 2D that it is printing at one point of time. You print a 2D, you keep on adding layers to it and make it into a 3D structure. And then, of course, the printing involving file transfer, positioning, and printing of design layer by layer. Again, even with your plastic printer, desktop, small printers, you do the exact same process. No different at all. Post-processing, of course, curing, surface finishing, and finally, you get the final path. That's your 2D path. Software will add paths on top of that to get to layer stacking to get your final object. Advantages, like I said, geometric freedom, flexibility, design ideal for architectural elements, reduction of construction time, labor demand, formwork free construction. This is another big advantage. Otherwise, if you want to build a concrete wall, you have to have a formwork, right? And then you pour the concrete inside the formwork. Now, the formwork, if I want a curved wall, I want to go and make a curved formwork. That curved formwork will probably cost me more than the concrete and the wall all put together, and more time, right? I have no design freedom. Whereas here, you will get a lot of design freedom. Topology optimization, you can optimize in whatever way you want. Challenges, limited reinforcement strategies. In your conventional concrete, that's what conventional concrete gives you so much. You put the steel, pour concrete over top of it, you're done. But now when you're printing how do you put rebar along with it? That's a challenge. Layer interfaces and anisotropy. You remember that your first assumption when you studied your concrete class was concrete is homogeneous and isotropic. Both of these out of the window now. No more homogeneity, no more isotropy, right? It is okay. It's not a bad thing. Aerospace guys, you ask aerospace guys, nobody deals with isotropy at all. They love an isotropy. They design an aircraft structure fundamentally knowing that they need an isotropy. Composite anisotropy is what they use to get the right properties in the right directions. So it's not something that is not undoable. But the design standards that you have, the codes and specifications that you have, everything is all homogenized around the homogeneity and isotropy idea. To overcome that is a challenge. Durability and exposure performance. There is no reason why 3D printed concrete will be less durable. There's no reason. Of course, there are more layers, right? There are more layers. So if the layer interfaces are not good, you will have problems. But if you control the interface, there's no reason it won't be different in terms of durability. So again, you need to do tests, you need to understand them, but it's not an insurmountable problem. But again, some people use that as a challenge. Design codes and standardization gaps is perhaps the most challenging aspect as of now. How do we let codes and standardization agencies accept the inherent differences in this technology and not treat it like a conventionally reinforced concrete? There are international standards organization ISO is coming up with sports. They have done it for walls now. Standard for 3D printed walls is there. Still, it's a very conservative standard, but nonetheless, a standard is there for walls, and they'll eventually come up with other shapes as well. Sustainability, circularity, climate goals. I talked about this. Um, you reduce the amount of material that you use, decarbonization, net zero, all of those will become much more easier if you take the material part in a controlled fashion. Geometric flexibility, this is what in Switzerland, they have done this art museum where it's, or open arts stadium where all the columns were made like this. This is in Netherlands, a concept for housing. This again, US Army's building on a platform. So they have this idea where they build in platforms and take it to places wherever they need. So it's building on a platform idea. All the nice fancy shapes that you can get, form and topology optimized shapes for a bridge, another externally pre-stressed concrete bridge here. There are a bunch of earthen structures that are coming up, building with clay and very little concrete to simulate ways in which people lived in the olden days. But if you look at this, that's a completely compression controlled structure. No tension at all anywhere, which means no reinforcement, right? No reinforcement, one half of the problem solved. But again, to print it in a way with overhangs and with geometry that is curving so much, you have to have material that is set on demand and things like that. A little more complicated. Topology optimization, we talked about this. Here is a pre-stress girder. You start with minimization of the weight and the stresses, and you eventually end up with this. You do all the final analysis. You end up, this would have otherwise been a rectangular beam. You see how much material has been saved, right? Can you ever make this structure in any way other than 3D printing? Perhaps no, not easily, right? You cannot do it definitely with a conventional casting method. It'll be very expensive. So that's the lab scale in Ghent in Belgium. They have printed that. Challenges again, reinforcement incorporation, failure prediction. Again, you cannot have this one size fits all the time. Now it's going to be very, very subjected to environmental conditions, wind, temperature, all of that. So how quickly can you build up? How much can you build up? Will all be dependent on all of those factors. You don't want to be building up something like this where material is squeezing out of everywhere. And then once you build something out and you take a cylinder, you don't want to be seeing this also, right? You see this, all the layer interfaces you can very clearly see here, where the two layers haven't joined really together, and you don't want that. Again, challenges, buildability, how high can you build? You don't want to be building up, building up. You don't want to be building up a 1,500 square feet perimeter wall. You don't want to be building up to 5 feet height and the whole thing falling like this, right? Um, and it's not even possible. Okay, it's concrete, fresh concrete, no problem. Let's take it down again, put it back in the mixer, work it. You can't do anything. It's gone. It's gone. So again, the control of the process is very important. Reinforcement challenges, we'll talk more about it. I talked about this. Durability issues, cracking. Uh, we'll talk a little bit more about this also. But again, one of the very critical challenges is about cracking, shrinkage and cracking. When you have so much of exposed area and when you have the material that's changing properties very quickly, very early. So what has been studied so far? If you look at lots of things that you find, lots of papers, if you look at it, printability, process feasibility, geometrical accuracy, strength, fresh state rheology, interlayer bond, anisotropy, global response, all of those well studied. Things gaining more attention now, I wouldn't say not studied, gaining more attention, durability related properties. So if you are looking for research topics, the right hand side is probably more about time dependent behavior and modeling of time dependent behavior to accurately predict the response. Reinforcing, shape, size, topology optimization, field scale, long term monitoring. We have very few field scale structures, long term monitoring of that to see how they are performing in real life. Standards and specification always will be a challenge for some more time. So, early 2000s transition from lab prototypes to full-scale systems. First large-scale house and demonstration projects have happened. Code-permitted and for-sale houses in the USA. So plenty of Icon built about 250 houses in Texas in a whole 3D printed park sort of thing. They said the houses will cost starting from $300,000 onwards. By the time they finished, the cheapest house was $500,000. It became very difficult for them to sell. I don't think they have sold the entire houses, but the company has, they had 75 or 80 people working for that company. Icon is now down to, I think, 10 people. They have laid off pretty much everybody. That's the first thing. First casualty when a company is suffering is people, right? People are the first casualty. So they laid off people, it's about 10 people now, and the company not sure they'll survive. SQ4D is another company that's printing houses as well. Printing housing communities and public projects in North America. They talked about housing communities where homelessness is a big issue in the United States, in the Western Hemisphere generally. So one of the ways that they are now looking at is to do what they call micro homes. So they print very small modular structures, 100 square feet, and be able to take it on the back of a truck, put it on a foundation, several of them put together to house people. For disaster relief, if you have a hurricane or tornado displacing hundreds of thousands of people, ready to deploy structures like this. They're thinking about it quite far away from really implementing. One of the biggest challenges, and we worked on this for quite some time, is the idea that 100 square feet house, a double white wall with the basic minimum specification compliance will be about 7,500 pounds divided by 2.2, that many kilograms. Okay, 100 square feet building with a small module for a toilet. Only 4 walls printed. You can flip it and you can put in ready-made walls on the other side and do it, whatever. But just 4 walls printed, this will be about 8,000 pounds, about 3,500 kilograms, 3.5 tons. Whereas most of the truck bed cranes that are available in the US that everybody uses, every contractor has a maximum capacity of 5 tons, 5 short tons or 5,000 pounds. So 5,000 pounds is a capacity. But if you want to make, and you can't live in something more than less than 100 square feet, right? It's going to be very small. So then what they wanted is to do, so we designed some concrete with lightweight aggregates and stuff to get it down to about 3,500, barely made to 3,500. So if you make enough of that, that could be one way. And again, San Francisco is a hotbed of homelessness. And so San Francisco has two faces. One is lots of homeless, and the other is people with billions of dollars income and money. So some of these wealthy billionaires are willing to make sure that their city looks better. Not many homeless are there. They're willing to put money, but again, what we have found out in the process of trying to do this is the biggest challenge with homelessness is not to build homes. The homeless people don't want a home. It's a psychological. It's a they love living in the street. They don't want to live in a home. They don't want to live in a you. We might think how nice it would be to give them a nice habitable shelter. They just don't want it, possibly because of life situations, drug issues, things that they have done. So, but not make it drink, right? You can make a house, but probably not make them live in those. Again, social housing projects in Europe again are gaining prominence. Europe also has lots of housing shortages. Move towards standard and specifications is the next one. Materials related challenges, variability of 3D printing, concrete, cementitious composites, all of this we will see in the next 4 days. Inconsistent processing methods, conflicting material properties demand at different stages. You need smooth flowing material at one instant. You need a hard material that can take the load immediately at the next instant. How do you balance those requirements? Lack of test methods. How do you test them? Can you do any, is there any ASTM standard to test it? Can I take the ASTM standard for compression testing of concrete and take a 3D printed concrete with layered structure and say that's a strength? Is it acceptable? Right? Again, lack of test methods will have to come in. Anisotropy, durability, tolerances. How much tolerance can you afford, or lack of tolerance can you afford? Now, you have to account for the fact that when you put in a soft material, when you put a layer on top of it, you might say, I don't want you to deform, but it is going to deform, right? Um, and there is short-term deformation, there's long-term creep. And that long-term is really not long-term. Even rheology, there is creep. There's creep in one day. So all of those things will have to be accounted for. Um, that's where we started. Bunch of properties that we will go through. Yeah, I'll just do this again. So what do we need? Extrudable, printable, open time. How much of open time you have? We'll talk about that. Setting and layer cycle time, vertical building rate. If I have to build up, say, um, a meter in 3 hours, right? How much area can I build up if I want to vertically build up a meter in 3 hours? How do you calculate that? Deformation as successive layers are added. Rheology measurements. We'll spend the first after today's afternoon on basic rheology, um, setting ourselves to understand how this will work out in the larger scheme of things. This is some of the first experiments that we did in 2015. We were all very excited. We're going to print this, and this is what we printed. We wanted to print a cube, and that's what we ended up with. Right? This is what we ended up with. Slumping of the mixture. Instability, warping. We're a little happy with, okay, at least it looks like a square. I can convince myself that's a square. But again, there's warping issues. Now you can see here, again, this is what I went to. First layer, by the time the second layer is built up, see the first layer dimension? Squeezed out completely, right? And now the shapes keep on changing as I go up. And then the edge retention, you see the shapes are all off because the edges are not proper. So lots of these problems can happen. If I can't even control a 5 centimeter size cube, how do I control a 50-meter long wall, a 20-meter long wall? So all of these critical elements, the materials that go in. Now, the other important thing with 3D printing is The printer is part of the problem and part of the solution. So in your regular concrete, you can take the concrete. I can test the concrete in the lab, 4,000 psi. I tested it. Go use your printer, use your mixer. I don't care if it's a Schwing's concrete mixer using your some other concrete mixer. I don't care. Mix it. This is it, right? Now, no, the printer is inherently the part of the story. How much pressure the ram is extruding, what kind of extrusion system, what's the dimensions of the blades in the extrusion system, how spaced they are. All of it influences how your concrete changes as it comes through the printer. So we'll have to think about that as well. So again, lots of different elements to think about. So a lot of different early properties, the rheology, which we will see, extrusion itself, uh, the system which is part of it, how do you know how much buildable it is, and all of this you will get an output, which is hopefully what you want. And then in that, you want to know what the flexural properties are, what the compressive properties are, what the quality is at later date. Um, Hardened properties, rheology principles, same idea. So some of these things we will see in the afternoon. So again, repeating a lot of things that I already talked about. Key gaps remain, but there are advances that we have made in lots of these areas. We will look at. We'll spend a lot of time on the advances that we have made because those are things that we can for sure say. We will point out the challenges so that you all can have careers in research or development or starting up companies solving those problems. That's what we'll do. Any questions? Everybody's hungry, looks like. We have we have 10 more minutes if you have questions, if you need clarifications on anything. Yes. Hmm. Okay. So what happens when you print something and then how do you test it, right? So if I print it, if the printer moves this way, and then I keep building on this way, and if I test the material this way versus this way versus this way, the properties are going to be different because the number of interfaces in each of those directions are going to be different. The quality of interface are going to be different. If I put one layer here, another layer on top versus one layer here and next layer here, the bond between these two layers and these two layers are not the same. So depending on how I test it, the properties are going to be different. So if I say that I have 30 megapascal concrete, 30 megapascal where, in which direction? The question then becomes, should you prescribe the dominant direction or the weakest direction? The weakest direction sometimes should be so weak that if you try to make the weakest dimension or weakest direction conform to standards, the strongest direction would be so over designed, you'll be wasting a lot of material, right? Your design will be suffering. How do we account for all of this? That's the basic question of anisotropy. That's one way. Now you put in reinforcement. For example, if you put in fibers, and we'll talk about it as we go through. As you fibers extrude through a nozzle, fibers have the tendency to align along the direction of printing. So now what you're getting is an oriented composite in the direction that you're printing with better properties in that direction. So can I think about being able to print in a way that I can align the fibers in the direction where I want the best properties? That now is a process variable that you have to think of. Other questions? Yes. For the horizontal elements like beam and slabs, like so you can print, for example, the topology optimized structures that I show are beams, right? They're basically beams. What they have done in that case is to make sure that you do analysis in a way that you take material away from where the load paths are not there. For example, you design for a uniformly distributed load or a point load, whichever way it is, Once you design for that load, you know where the load paths are, and along the load paths, you put the material. Maybe put a fiber reinforced material to take care of tension also in that direction, and not have materials in those parts where you don't want. That's the best way. Now, otherwise, if you want to design a beam to span a column, then you really need reinforcement if you're doing a prismatic member, right? Then it becomes a problem that we haven't yet solved. So the beam strategy works well when you can optimize the geometry in such a way that you can take away material, you can reinforce, you can print thicker in directions where you actually want a load carrying, and not have material in other directions like I showed in those beams. That's where we are. So I have seen some latest printing where people have printed some overhanging slabs where they have done overhangs from both sides, and it looks with fiber reinforced concrete and it looks nice. But I don't know the details. But there are efforts where people are trying to do that now. Somebody else?
Maybe it is too early to ask that question. Like you were saying about spraying of like aggregates between the mortars. Like how is it not going to affect the layers when they are kind of placing the aggregates and how it will.
Yeah. So what this is pre-placed aggregate concrete is a technology that's already there. So you know what this is called? It's called pre-packed aggregate concrete. So if you want very high aggregate volume fractions, especially for shrinkage control, and to reduce the paste volume for lots of different reasons, what you do is you have a layer of mortar and then you spread the layer of aggregate, and then you again spread a layer of concrete. So it's basically like a layered composite construction. And aggregates, once you layer them and compact them, they are anyway much stronger than the paste. So basically, what the paste is doing is to just forming a glue between these layers. They're doing the same philosophy, and especially when you have a compression member, you have no problem at all. Aggregate is doing most of the work. This is like exactly like doing a brick laying, right? Brick with mortar to lay them. This is exactly the same thing.
So is it not going to deform the.
Well, you have to control it in such a way that your mortar also is probably stiff enough, and then you place the aggregate. So yeah, it will require its own rheological controls. Yes. Lunchtime looks like everybody is eager.
Yeah. So I have more questions. Always interact with the.
Yeah.
I would suggest perhaps asking while he's presenting. Ask a while.
Yeah, stop me while I'm presenting. Don't, no problem. Stop me if you have a question, so that I'll stop in between, because I need some breath also in between. So I'll stop. But ask me in between, stop in between. That way we can have a more interactive session. Otherwise, 5 days is boring, guys. Remember, right? 5 days will become really boring for you and for me. So please interact and make it more of a two-way traffic than a one-way traffic. Makes it a little easy on us as well.
Okay, so we'll quick break here. You notice the lunchtime is at 12:30.